Hello everyone, this is Professor Iris Miano with a Day 24 lecture for Math 2 on section 7.3 and 7.4. That's law of cosines and area of a triangle. Okay, so let's just hit the ground running. We already introduced the law of sines in the previous lecture video, in which case we outlined 4 specific cases of types of triangles that could be having incomplete information, that had enough information given in order to do what's called solve the triangle, which is to determine every interior angle measurement and every edge length. Okay, so for law of cosines, we're going to focus on cases 3 and 4 in which we have 2 side lengths known with an included angle, or all 3 sides are known. And law of cosines is pretty much just working with some variation of this formula where you have the square of one side of a triangle equals the sum of the squares of the other 2 sides minus twice their product times the cosine of their included angle. So if you don't have any of the angle measures, like in case 4, then your cosine of either C, B, or A, depending on which version of this relationship you're using, is going to be unknown. Otherwise, you will want to use the version in which you have the unknown side length squared, and then you can solve for it. Okay, there's a couple of figures off to the side here just to illustrate some of the elements here. As far as like coming up with derivation, I don't want to spend a lot of time on that. That's, I feel like, a discussion for another time. What I do want to spend our time working on is understanding how to use this relationship here, the law of sines, which has 3 different versions of it depending on what either angle or side length you want to solve for. Okay, so let's go ahead and start off with example number 10, in which we are given angle A, which is the 30-degree angle here. Notice opposite side length lowercase a is unknown. And we are given side lengths lowercase b and c of 3 and 4 respectively. And then angles b and c are unknown to us at the time. Okay, so we need to bust out law of cosines, and I would start by finding the value of A, because it is, yeah, so that's the unknown length, right? So law of cosines with A squared being on one side of the equation leaves the square of the other 2 sides summed together minus 2 times their product times the cosine of the included angle. Okay, so that's just me writing down the appropriate version of law of cosines that I want to start off with in regard to solving this triangle in number 10. That's going to be this bottom one right here. Okay, so, and I recommend that you write it down in its generic format with A, B's, and C's every time you use it, so that by the time the exam rolls around on this material, you have it like deeply embedded into your heart. Okay, so let's go ahead and plug in 3 for B, 4 for C, and cosine of, it'll be 30 degrees. Now that's a famous angle in unit circles, so we can surmise straight away that that's going to take on a value of root 3 over 2. So, you know, doing a bit of simplification here, we will get 9 plus 16 minus 2 times 3 times 4 is going to give me 12, and then root 3 over 2 is also in the mix. Okay. So I can cancel, oh, excuse me, oh, 3 times 4 is 12, but there's still a factor of 2. Oh, my bad. Hold on, let me make a quick adjustment here. That wasn't a 12 out in front, that should be a 24. Check my notes, and luckily they are correct in my notes. Cool. Then you're going to cancel out I'm a factor of 2, and it's going to leave a 12. I guess that's what I was focusing on. Cool, cool, cool. So 9 plus 24 plus 16 is 25, minus 12 root 3s equals a squared. Okay, now this can't be simplified any further, but what we can do in order to get a all the way by itself is to take the principal square root of the other side. And at this point, you'll just want to plug this into your calculator and get a decimal approximation. And the convention is to bring it out to the second decimal place. So if you type all this in and it's good to go, you don't make any syntax errors, you should get a having a value of 2.05. Okay, so that's A. Now we still need to get angles C and B, okay? So then the next step is going to be using, of course, law of cosines again, or that's one way that you could do it. So, and because we're working in the section referring to the law of cosines, that's the spirit in which we're supposed to be working. So I'm going to go ahead and continue with that. And I'm going to use the c squared version of it because I want to find, for no particular reason, the value of capital C. You could also do a route where you find B, and then we'll just use the fact that the interior angles of any triangle sum to 180 degrees to get the other last angle, and then we'll have that triangle all solved. So again, I'm just going to use a different version. I'm going to actually change up the color just to make it super clear that I'm doing a different calculation here. I'm going to use c squared equals a squared plus b squared minus 2ab, excuse me, 2ab cosine c. Okay, so I don't know what C is, but I know what all these other things are. So you can either plug in the values now and then solve for C, or you can solve for C first and then plug in all the values, which for no particular reason I decided to algebraically solve for C, which is to say I subtracted a squared and b squared from both sides and then divided both sides by negative 2ab, getting the following. So c squared, subtract a squared, subtract b squared. And then you'll have just this on one side of the equation, right? So we'll want to divide by negative 2ab, and that'll give you cosine of c. Then you'll take the cosine inverse of both sides, or just rewrite it in terms of the cosine inverse, and then you'll have exactly what you can plug into your calculator. C squared minus a squared minus b squared all over negative 2ab. And that equals C, which again, like, what are you actually plugging in there? Well, you'll plug in the appropriate numbers, which are still, for lowercase c, it's, in fact, I can just adjust these accordingly, like so. What are the actual values? C is 4, right? So that's 4 squared minus, what was a squared? Oh, a, yeah, that was this bit right here. So that would just be 25 minus 12 root 3. Wow, okay. Let me give myself some more room there. Minus 25 minus 12 root 3, and then minus b squared, and b is 3, minus 3 squared, and then divided by negative 2 times a, which is that square root of 25 minus 12 root 3s, and then times 3 as well, so times 3 down below. You put all this into your calculator inside of an inverse cosine, and you'll get C is about, let's see, 103.1 degrees. So you'll take this 103.1 degrees, add it to the 30 degrees that's already there, take that sum, so it's 133.1 degrees, subtract that from 180, and then you will get what? Let's do this color. Then you'll get B, therefore, equals 46.9 degrees. So here is your A, lowercase a, capital B, capital C value. Cool, cool, cool. All right, moving on to the next. So in this first case, for number 10, we had two sides and an included angle known, the SAS or SAS situation. Here we have an SSS, where the only thing that we know are the four side lengths. Okay, so when that is your deal, we want to, it doesn't matter which, actually for this one, there's a special thing happening. Do you guys notice that there's two side lengths that have the same measure? That makes this triangle an isosceles triangle. And so if you know the relationship from your geometry class between the opposite sides and their corresponding angles, you'll know that if you have in a triangle two congruent sides, then their opposite angles are also going to be congruent to each other. So that means measure of angle A, hold on, let me erase that real quick. Measure of angle A is going to be equal to the measure of angle C, because those two angles are opposite of two side lengths that are equal to each other. Okay, so let's keep that in mind, and I think then we should probably find the measure of angle B, and then we'll just subtract that from 180 divided by 2, and that will give us not only measure angle A but C to boot, because they're equal to each other. Okay, so then what should I do? Well, let's go ahead and find, using this version of the law of cosines, the value of B, capital B, that is the angle measure. Okay, so we can, just for funsies, let's go ahead and just plug in the numbers here, and then we'll solve for B after the fact. I think people might enjoy that a little bit better than going through this rigmarole here, solving it all algebraically and then typing in your calculator. Maybe not so fun. Okay, so B is 3, so we'll have 3 squared here, equals A is 4, and C is 4. Okay, so we'll get 9 equals 16 plus 16 is 32. I'll just go ahead and add those together on the fly. 2 times 4 times 4, that's going to be another 32, if I'm not mistaken. Cosine B. Let's subtract 32 from both sides, and then also divide by negative 32. And when you do that, you're going to get negative 23 over 32. So those negative signs will cancel out, and you'll have 23 over 32 equals cosine B. So now it's just a matter of taking the cosine inverse of both sides. So that means cosine inverse of 23 over 32 is going to give us the value of B, which is rounded to the nearest tenth of a degree. It'll be 44.0 degrees. That's fun. Okay, so take this 44 and subtract it from 180, and you will get 136. So 136 degrees is the amount of degrees left for both A and C. A and C are equal to each other, so it lends itself to just dividing that 136 in half. So 136 divided by 2 equals 68. So 68 degrees, therefore, is A and C. I'll box them all up together. And B. Great. Fantastic. That is that. Okay, so this is all well and good when you have a picture at your disposal as far as figuring out who is where and what to do. What happens if you don't have a picture? Well, you just draw yourself one. It's no big whoop. Like so. Let's say you are given this information, side lengths B and C are 4 and 1 respectively, and you have a measure A that's included of 120 degrees. So, you know, that could look like this, let's just say. Lowercase b, let's say, is here, so that's 4. C is here, 1. So that means the C angle has to be right there, and B angle has to be here. A has to be there, and it's specifically 120 degrees, and we don't know the length of side A, so we'll put a lowercase a directly across the way from it. Okay, it's supposed to be looking more like a C. Okay, that looks fine. Great. So where do we want to go with this? Well, we need to find lowercase a, capital B, and capital C, but where should we begin? Probably with lowercase a. So I'm going to put down the law of cosines relationship for a, or as setting equal to a squared, that is. A squared equals b squared plus c squared minus 2bc cosine of a. And then fill it in, basically. Plug in the values. So b is a 4, so it's 4 squared here, plus 1 squared there, minus 2 times 4 times 1. Cosine of 120 degrees. 120 degrees is famous, but the cosine of that is going to give us a negative 1/2 factor. So let's do some simplification. We'll get 16 here, 1 there, minus 8 times 1/2. Sorry, negative 1/2. Boop and boop. Let me make it more clear that that's negative. Great. Okay, so notice that negative signs are going to cancel here and here. Boom, boom. This is going to become addition, and it's going to be addition of a 4, no longer an 8 times a 1/2. So all that cancels out, and then we're left with, that's 17 plus 4 is 21. But remember, this was equal to a squared the whole time. So it's not that a equals 21. Oops. It's that a squared equals 21. So that a, therefore, equals the square root of 21, which is approximately 4.58. Okay. Cool. So we'll use the square root of 21 for any future calculations because we want to be as accurate as possible and have as few instances of rounded off error as we can get. So now let's go ahead and I'm going to choose to use the B version of the law of cosines. For no particular reason, you could use the C version, or the C squared version, as you may like to call it. I'm choosing to use the B one. And we're going to use this in order to solve for the value of angle B, capital B, this one right here, okay? Great. So plug in what you know. B is 4 squared. A, we just did that, so that's square root of 21 squared. Those are going to cancel. Plus 1 squared minus 2 times root 21 times 1 cosine of B. So this is fun, how this will cancel out, cancel, and you'll get 16, oops, let's be consistent here. 16 equals 21 plus 1 minus 2 times 21, root 21 that is, cosine B. So it's 22. We're going to subtract 22 from the 16 to get negative 6, but then also divide it by the negative 2 over 21, and we will get 3 over root 21. It's going to be cosine B. And I know what you're thinking. You're probably like, oh my god, we need to rationalize this denominator. Go ahead and just cosine inverse this bad boy. And you're going to get cosine inverse is 3 over root 21. And put that in your calculator. I promise your calculator is not going to mind that you have a radical in the denominator. And you should get that equals, obviously that equals B, which is approximately 49.1 degrees. Okay, so if this is 49.1 degrees, then we just take the 49.1, the 120, and we subtract both of those from 180, and that will glean for us that C equals 10.9 degrees. And that's a wrap on that one. So what's nice about this law of cosines business is that when you have two sides and an included angle, you just have to find the one remaining side and one of the angles, and then the last one just kind of falls into your lap by virtue of knowing that the interior angle sum for any triangle has to be 180 degrees total. Okay, let's do this again with no originally given picture, but we know that we have three sides, right? So we're just going to make a generic triangle, make sides 3, 4, 6, excuse me, and just recognize that the opposite angles are going to be labeled according to these letters that were given. So the 4 side, its opposite angle is going to be capital A. The 3 side, its opposite angle is going to be capital B. And then this last one will be C, duh, because, you know, process of elimination. Cool. So where do we want to start with this? It doesn't really matter. I chose for no particular reason to go the a squared version of law of cosine. So I said a squared equals b squared plus c squared minus 2bc cosine of a. All right. And we're going to do this to figure out what the value of the cosine of A is, okay? And that'll be, so I'm going to use the structure that I kind of figured out last time, which is to say that if I solve for A, it looks like this. Cosine inverse of A squared minus B squared minus C squared all over 2bc, negative 2bc that is. That's going to give me A, and now I can just plug and chug. Here we go. So the thing that you're actually plugging into your calculator will be, what's A again? 4 squared minus 3 squared minus 6 squared all over negative 2 times 3 times 6. Okay, that equals A. We could do some more simplification before we reach for our calculator though, which will be cosine inverse of 16 minus 9 minus 36 all over negative 36. And then what'll that give me in the numerator? That's a 29, negative 29 if I'm not mistaken. Over negative 36 will settle down to a 29 over 36. So this is what you'll type into your calculator, and it'll give you an A value that's approximately 36.6 degrees. Oh, sorry, 36.3 degrees is what I meant. And so remember, the convention for measurements in degrees is to round to the nearest tenth of a degree, and the convention for any side length is hundredths of whatever the length measurement is. Okay, great. So there's that. I want to use the same kind of structure. I'll get a new color going. How about this pretty purple color? And but we're gonna go solve for B, and the way B can be solved for like very quickly is to let me just draw a little vertical line there. It's the cosine inverse of B squared minus C squared minus A squared all over negative 2 AC. Yes. That's going to give you B. And once you have B, you can, you know, add up A and B and subtract that from 180, and then you'll get C. Cool. So let's go ahead and plug and chug. So that'll be 9 minus 16. I'm going to just jump some 36 over -2 times 4 times 6 equals b, and so that'll give you that you're going to cosine inverse. You simplify that down some more and you'll get 43 over 48. And the negatives will cancel. So that'll give you b, which is approximately 26.4 degrees. Okay, add 26.4 to 36.3, and that will give you that C is therefore approximately 117.3 degrees. That is that. A, B, C, we've got all the angles. And we only ever have to use the law of cosines twice. If you're doing it a third time, you're doing too much work. Because you can always, if you're using law of cosines, figure out what the last angle should be by just knowing that the interior angle sum of any triangle is 180 degrees. Okay, moving on. So let's do a word problem. I thought this one was kind of interesting, identifying remains. So this is associated with like paleontology, or I guess maybe it could be what's it called? Archaeology, or, well, no, it would be, yeah, archaeology, sure. And or like forensic science, right? Could be attributed to what's going on here. In any event, let me read the prompt for you. This is number 52. It says, so it's referring to a Purkate triangle that was presented in the previous problem. We don't actually need that information. We just need some lengths and an included angle in order to figure out parts A, and then part B is just very super simple, you know, just painfully obvious question. You'll see. Okay, so it says, like the Purkate triangle in problem 51, the metric triangle is located at the proximal end of the femur and has been used to identify the gender of fragmented skeletal remains. See the figure. Okay, for part A, they're saying that AC, so that's this length right here, is 48.8 millimeters. So I'm going to go ahead and label that there. BC is 62.2 millimeters. So we don't know A to B, but we're going to find the length of it. Also recognizing they gave us the angle measure for C, which is right here, of 89 degrees. So we have two lengths and an included angle, so therefore we could solve the triangle using law of cosines, and we're going to do it to find the length of AB. Okay, so let's let the length of AB be lowercase c, just so that we have, you know, the ability to use this formula. Oops, got a little wonky there with my 2. Let's try that one more time. So that'll be c squared equals a squared plus b squared minus 2ab cosine c, in which a, lowercase a and lowercase b, are 62.2 and 48.8 respectively. So I will get c squared equals 60. A is, yeah, 62.2 squared plus 48.8 squared minus 2 times 62.2. You know what? Hold up. Let me actually, oh, can I just pick this up and take it somewhere else? Is that how this works? Oh crap, hold on. Try that again. And let me see if this can just be moved over. It totally can. Look at that. Woo! Nice. Okay, so yes, I'm gonna reference this formula over here, but I'm gonna continue my work over there because I was running out of room. Cool. 2 times 62.2 times what? 48.8 times the cosine of C. Oh, which is 89 degrees. So let's go ahead and replace C with 89 degrees. And more or less you will just plug that into your calculator, and that'll give you C squared. So if you want to get C, okay, it's just a matter of, let's erase this squared right there and put a big old square root around this whole darn thing, right? Cool. So type this into your calculator, and what does the calculator give you? Calculator gives you that C equals 78.4 millimeters. Okay, cool. So that's this distance, what is it called? Proximal end of the femur is the metric triangle is located at the proximal end of the femur. It's been used to identify. Okay, so this length from A to B right here. So the ball socket joint to this other edge, I don't know what it's called. If you determine that length, you can figure out if the remains likely come from a female person or a male person. So here, enter part B. This is part A. If AB, the length of line segment AB, is less than 80 millimeters, typically indicates a female, and if it's greater than 100 millimeters, it typically indicates a male. Which gender, if any, would be identified from the measurements in part A? Well, I don't mean to be too flippant, but obviously we're talking about a female, I would think, given the circumstances of the restrictions on the measurement. It's a, 78.4 is less than 80, so likely a female. And that's it for that one. Okay, so now I would like to enter into section 7.4 and do a few triangle area examples. So we're given some new formulas here. I'll scroll down so we can see those. All right. So obviously we've all been introduced at some point to the super famous, quintessential area formula for a triangle, which is that its area is going to be half of its base times its height, or base times height over 2, or some such variation that has an equivalent value, okay, to that. Okay, but we want to think about this in terms of side lengths and interior angle measures, because you won't always know the height of your triangle, right, from the given information that you have. So you might be given side lengths and interior angle measures, and if that's the case, you can use these slight modifications to the original area formula in order to capture that. And then furthermore, if you have so this is if you have two side lengths and the included angle, 2 side lengths and the included angle. This is the formula that you'll use. And if you have just the 3 sides, you can use this formula, in which you have to make a preliminary calculation, or it is recommended you make a preliminary calculation on this value S, which is half the sum of the side lengths. So once you have that, you plug that into the square root of itself, S, times the difference between each individual side length and S. Okay, so there's 4 factors total, technically. That's Huron's formula. Okay, so let's practice using these formulas. Here is our first triangle. Notice that we have 2 side lengths given and an included angle, so it's perfect for either one. So one of these 3 versions of the area of a triangle formula given a SAS triangle, so to speak, a side angle side. Okay, so since angle A is given, and excuse me, here we go. I'm going to, sorry, make sure that I'm open to the correct page. There we are. There we are. I'm going to reference the appropriate formula, which is as follows. K, capital K, is for some reason the variable associated with area of a triangle. Not really sure where they got that from. In any event, we'll use it. Equal to 1/2 lowercase b, lowercase c, times the sine of A. Okay, because this is the info that we have, and you just throw it all in this formula. I mean, really, as long as you got a functioning calculator at your disposal, couldn't get much easier. Okay, so here, this 2 and this 4 are going to cancel out. And leave just a factor of 2 behind there. This one's done. So it's 6 times sine 30. Well, what's sine 30? It's 1/2. Oops, this. Hold up. 6 times 1/2, which is the sine of 30 degrees, and you're going to get 3. Now this is area, folks. So usually if there's some units associated with the sign links, you would square the units in regard to presenting your final answer. This is not necessary by any means. I just want us to recognize that the units, if they were given to us, would be squared, okay? So I'm going to always put units squared generically at the end of our work here, okay? So that means the area of the triangle number 8 is 3 square units, 3 units squared, however you like to say it. Okay, so that's that. That's all you need to do. You just pick the appropriate version of the area formula, plug in the numbers, Bob's your uncle. Let's do this again for number 10. This time we have side links 2 and 5, which are lowercase a and lowercase c respectively, and angle B is 20 degrees. Okay. So use this version of the area formula, 1/2 AC cosine of B. Okay, and plug and chug. A this time is a 2. C is a 5. And we are taking then the cosine of 20 degrees, which is not something that I know off the top of my head. So I'm definitely going to rely on some calculator bits here, and I'm going to give my approximate answer rounded to the nearest 100th, because it's an area based on side lengths, which are conventionally rounded to the nearest 100th. So that'll give me 1.71 units squared. Cool. Yeah, there's not much to it once you know and learn the formula. Okay. Let's have another example, though, here for number 14, where we're referencing an actual triangle figure. And notice that what we are given is no longer 2 sides and an included angle, but all 3 side lengths. So whenever this is the case, and you're going to find its area, you first need to calculate that S value, okay? Which is 1/2 times the sum of all of the side lengths, okay? Which for this particular is 1/2 times the quantity 4 plus 4 plus 3. Oh, I guess technically 3 is the B value, so I want to be consistent here. Hold it. Plus 3 plus 4. Whatevs. Addition's a commutative. That'll be 1/2 times 11. Which is what, 11 halves, or 5.5 if you like. I like to use the decimal version of this when it doesn't divide evenly, so that's fine. You do you. Okay, so K, the area formula in this case will be, remember, S times S minus A times S minus B times S minus C. So for this particular instance, that'll be the square root of 5.5 times 1.5, because that's 5.5 minus 4. 2.5, because that's 5.5 minus 3, and then 1.5 again, because that's 5.5 minus that other 4 factor. and you will get, weirdly enough, approximately, you type this into your calculator, syntax is all good, you should get 5.56 units squared. Okay. Great. Now, that was good having pictures. What if you don't have a picture? Draw yourself a picture. No biggie. Some generic triangle, doesn't matter. Slap on a 4, slap on a 1, slap on a, where's A go? Okay, so B is 4, right? So the opposite angle needs to be capital B, 1 needs to be capital C. So here's A, 120 degrees. Okay. And then we've got to, oh, let me clean that up a little bit. That's a little sloppy. It's 120 degrees. Better. Okay, so what do we need to find here? We need to find the appropriate version of the K area formula. So here it'll be 1/2 BC sine of A. Okay, so plug in the numbers. 1/2 times 4 times 1 times the sine of 120 degrees. Cool. So let's cancel out some common factors here. We'll be left with 2 times sine of 120. Sine of 120 is root 3 over 2. So 2 times, check this out, 2 times root 3 over 2. Those 2's are going to cancel. And you'll have root 3 is the area, square root of 3, which is approximately 1.73. And slap on some square units, however generic. Okay, a few more to go here, folks. Relatively short lecture video, I think. All right, here we've got 3 side lengths. 4, 3, 6, sure. And let's go ahead and recognize that A would be here opposite the side length of 4, and then B would be there. C here. Okay, so what we need to do is to find the area. We first need to calculate that S value. Now, why do we do that? Because what we're given is the 3 side lengths. So whenever that's the case, you got to calculate that S, which is again 1/2 times the sum of the 3 sides, which is 1/2 times 4 plus 3 plus 6, which is half of 13. Which is what, 13 halves, or 6.5, is that what I put? Yeah, 6.5. So therefore the K value, which I won't rewrite that whole formula again, I'm just going to put in the values of S, which is 6.5, A minus S is 2.5, hold up. Sorry. Then 3.5 and 0.5 are those difference values. What will your calculator give you? 5.33 units squared. Okay, hold on just a moment. Okay, we're back. Sorry for that brief interruption. We just needed some, my daughter needed some bathroom assistance. Now, I know that's TMI. I won't go into more detail than that. Great, but that's it for that particular problem. And we can move on to the next, which are our I got 2 application problems here for us. One of them is the dimensions of home plate. Hi, sweetie pie. Can you give me 10 more minutes?
No, what's your IT?
Okay, let's hurry up and punch this one out so you guys can get to work on it, and I can address my daughter who very much wants my attention. Okay, dimensions of home plate are given. If for any major league baseball stadium are shown, find the area of home plate. Okay, so what I did here is I did the thing that probably comes very naturally to all of you seeing this figure. I cut it into a triangle and a rectangle. So just kind of like adding a little line here, a dashed line, however you want. And so that gives me one triangle in which I have all three side lengths. Two of them are 12 inches. And then this one across here is the same length as the bottom of this now rectangle that I've separated this onto. So that'll be a 17. So then I can use the all three sides formula to first calculate S, which is going to be 1/2 of 12 plus 12 plus 17, which boop-a-doop-doop gives you 41 over 2, half of 41, or I'll just go ahead and straight away put 20.5. Okay, so now we can get the area of this rectangle by putting in the square root of 20.5 times 8.5, 8.5, and 3.5, which are this S value having subtracted off 12, 12, and 17 respectively. So you put that into your calculator and you will get 71.99956.597. Okay, and I'm giving myself a lot of significant figures here just because I know I'm going to have to add this to the area of this rectangle, which is, you know, easy enough to find. The area of a rectangle, so I'll just kind of make up my own notation there, is base times height, which is 17 times 8.5 for this one. So that'll be 144.5, if I'm not mistaken. So we take these two values and we, I thought I clicked that. Hold on. I erased it. Thank you. Take this and we take this and we add them together, and then we round it off to the nearest 100th, and we will get that the area is 216.5. For some reason they rounded off to the nearest 10th in the answer key. I'm not really sure why they would do that. It's not wrong to take it out to the 100th place unless of course they specifically ask you not to do so. And we did have specific units here of inches, so go ahead and make sure that you display those in your final answer. Okay, last one, Bermuda Triangle. The Bermuda Triangle is roughly defined by Hamilton, Bermuda, San Juan, Puerto Rico, and Fort Lauderdale, Florida. The distances from Hamilton to Fort Lauderdale to San Juan, from San Juan to Hamilton are approximately 1,028, 1,046, and 965 miles, respectively. Ignoring the curvature of the Earth, approximate the area of the Bermuda Triangle. Boy, it would be nice if we had a figure, wouldn't it? So let's go ahead and label the edges as here's Hamilton, here's San Juan, and here is Fort Lauderdale. Okay, and the corresponding lengths are 965 miles from Hamilton to San Juan, 1,046 miles from San Juan to Fort Lauderdale, and 1,028 miles from Fort Lauderdale to Hamilton. Okay, so let's bust out our S formula, which we know we're going to need because finding the area of this triangle, only knowing the lengths of the sides, is going to require that we first calculate S and do the square root of S times S minus A times S minus B times S minus C. That chestnut. Okay, so here we're going to add up all of the side lengths and then take it by half to find the value of S. It's supposed to be 28. 1046. Okay, so that ends up being 1,519.5 is your S value. So then your K value here is the square root of exactly that value, and then all of the differences between that value and the side lengths, which give you 500. sorry, let's clean that up a little bit. 544.5. 554.5. I'm so sorry. Yikes. Let me just do a better job of looking at my notes. 554.5. 491.5. And lastly, 473.5. Type that very carefully into your calculator and you will get that the area is approximately 442,816 miles squared, square miles. And they rounded that value to the nearest square mile, which is somewhat against convention, but there you have it. Okay, that's all that I have planned for this lecture video. Let's definitely continue the discussion in class. I'd be delighted to do more demonstrations per your request. See you then.